We just got done learning how to make confidence intervals for a population proportion P in section 8.2. In section 8.3, we're going to learn how you do the same sort of concept, make a confidence interval. But instead of making it for a population proportion, we're going to make a confidence interval for a population mean. And like I told you guys in earlier videos, these two variables, parameters P and mu, are kind of our big two. We're going to get really, really good at dealing with problems with P and also with mu. The reason that we focus on these two so much is they handle the two different kinds of variables that we encounter in statistics. If you have a variable that's going to be a categorical variable, so you have categories like who are you going to vote for, or what's your favorite color, or whatever, you can turn that into a percentage. So you can look at this percent of people think blue is the best color. So any variable that is categorical can be analyzed with P. And then if you have a variable that's numeric, how many hours of sleep did you get last night? How many hours do you get on average? Whatever you want to say. If your variable is going to be quantitative, you can analyze it with mu. So we get really good at P and at mu because no matter what kind of variable you have, categorical or quantitative, one of those two things will work. Okay, so when I ask you to do one of these four-step problems where there's a lot going on and just, oh gosh, you have to make an interval, interpret it, do all this stuff, it's going to be either a P or a mu problem, and you need to be able to keep straight and identify which of the two situations it is. There are tons of other variables out there that you could still make confidence intervals on. It's not like these are the only two options possible, but they're the ones we focus on the most. Were you to be asked to make a confidence interval for sigma or something like that, it would be like an extension above and beyond kind of a question. But these are our big two. So we learned P. Now we're going to learn the rules and investigate mu. So let's go ahead and start out by looking at a little example here, and we're going to use an internet applet to get at a few kind of key points. So we've got this farmer, and he wants to figure out the average weight of all of the tomatoes on his farm. So measuring every single tomato, gonna take forever, not really an option to do that. So instead, they're gonna take a random sample, and then they're gonna build a confidence interval based on that sample. So he picks a relatively small sample of 4 tomatoes, calculates X bar, the sample mean, makes a 99% confidence interval for mu. And then they say, okay, suppose, this is for the investigative purposes, he wouldn't know this in real life, but in reality, the tomatoes on his farm are normally distributed with a mean of 100 and a standard deviation of 40. So those are the actual stats for the tomatoes that he wouldn't know when he was doing the problem. So we are going to use an applet that you guys saw earlier in this chapter to help illustrate what's going on here. And remember that when you build a confidence interval in general, the setup is here at the very bottom. You start with your statistic, and then you add or subtract your margin of error, which is these two pieces, critical value times standard error. And I'm going to show you guys 3 different possible ways we could make a confidence interval for this problem. So when you build a confidence interval, you start out with your statistic. If we're making a confidence interval for the average, we're making confidence intervals for mu now, not P. Our statistic that we start with is going to be X bar. That was that sign that I was wearing at the beginning of the chapter. When you want to do a problem on a mean, you start with your sample mean X bar. Then you're going to add and subtract your critical value. So for our critical value, I'm just going to go ahead and use Z star because we did learn that X bar was approximately normal. There were 2 ways X bar could be approximately normal. One was we were looking at whether the sample size was at least 30. So if it was, then the sampling distribution of X bar is approximately normal. The other option was that our population was normal, and it said that in the problem, actually. It said that the tomatoes are normally distributed. So we're going to use a Z star here. And what is the formula for the standard deviation or standard error of a X bar sampling distribution? You might remember this formula, you hopefully do, but the formula we used for the standard deviation in that context was this guy right here. It was your standard deviation divided by the square root of n. And then we could plug in our numbers from the problem and we could make this work. But I'm going to switch over to my applet right here. I have this set up with the mean of 100, the standard deviation of 40, sample size is 4, and we are going to do a 99% confidence interval. And I'm going to go ahead and show you guys, okay, there's my sample. My sample mean was a little over 120. It says it was 129. But when I reach out my arms, I catch the right answer of 100. So my interval worked out. And I'm going to do these 100 at a time here. And we're going to look at how good of a job we are doing. So I just did 100 of those right there, and there was one that missed out of those 100 different intervals generated. So that's good. That was 99%. But we should keep going to get enough data to make sure in the long run that is how it works out. And as I do this for a while, do 1,000 more, you end up finding that it does seem to level out at 99. So that's good. That's what we want to happen because we had a 99% confidence interval. And it worked 99% of the time over many, many trials, okay? So on this first example here, I'm going to put a happy face. Happy face because this method works like we would want it to, okay? So we are pleased with this. This gives us the success rate that we're supposed to have. But there is an issue with this first blue method up here. Think if you can figure out what it would be. It kind of relates to in the other problems last section, how we didn't know P. Think about what we wouldn't know in this little formula right there. The answer to that is if we're trying to make an interval for mu, we don't know the average, the mean for the population. How are we going to know the standard deviation of the population? If we don't know the mean for the population, how could we know real sigma? This is unrealistic that we would actually know real sigma. So it's unrealistic. So I'm going to put like a little quizzical face right here. What does quizzical look like? I'm not really sure. Maybe something like that. Because we don't know sigma. If you don't know the actual mean, how are you ever going to know the actual standard deviation? So this method works in some crazy sequence of events. If you knew the actual standard deviation, awesome, you're good to go. But it's not realistic that you would know sigma when we're trying to find mu, okay? Well, that's all right. If we look at problems in the last section, we had that going on with P, where we didn't know P. So what did we do? We threw P hats in there, and it worked out great. So what I'm going to do with this problem, method 2, I'm going to keep things exactly the same here, x bar plus or minus z star. And then all I'm going to do is I'm going to sub in S, our sample standard deviation, in place of the population standard deviation. You just substitute in, out of my 4 tomatoes, I would just find their standard deviation, and I would use that S in my formula. So my internet applet is going to show you what happens with that. So we're resetting now. And this time, what I want, oh, now did that clear everything here? Nice. Okay, what I want to do this time is I want to switch it to a Z, still using Z star, but I'm using S instead of sigma. Everything else is the same. I'm going to jump and I'll do 100 right away here. And if you look at this 100, it looks like 95 of them out of 100 worked, and we have a 99% confidence level. Do it again. That time I had 91%. 94, 88, 97, 93, 92. So I'm not doing so hot right here. I'm going to jump this up to like 1,000 and do a couple more times. So I've just done 24,000 intervals, 24,000 samples of 4 tomatoes, and I built intervals based on them. At a 99% confidence level, I'm only succeeding about 92% of the time. So my interval is very much not working as advertised. I would expect 99% of them to be successful, but I'm only getting 92, okay? So this second method, for whatever reason, does not work like it is supposed to, okay? The capture rate or the success rate is too low. Success rates is lower than advertised. Why is that happening? Well, last section, what we did is we took problems and we had P in them, and we were like, oh, P, get out of here. We don't know you. We're going to use P hats instead. I'm oversimplifying a little bit here, but the reason that's okay is because we spent time in chapter 7 analyzing P hat, and we found that P hat's sampling distribution is approximately normal if conditions are met. So P hat was real good. We like P hat because P hat follows an approximately normal sampling distribution. S, on the other hand, last chapter 7, we didn't talk about the sampling distribution of S. S, you can't just assume any random thing is going to be normal. We know X bar looks normal. We know P hat looks normal. Their graphs do. But S, there's no guarantee it is. And actually, the distribution of S is actually skewed to the right. So we're subbing in S for sigma. And S plays by different rules. So when we do this, it breaks our confidence level. It doesn't work like it's supposed to. So we're going to do one more thing. Our third method, we're going to keep it the same. But since P hat, like with P hat problems, that was still approximately normal, we were good. With S right here, S does not follow an approximately normal distribution. We are instead going to use a new distribution called the T distribution. So the T distribution is going to be brand new to us in this video. I'm just going to, for now, write down T star instead of Z star, and then I'm going to use S like I did before. So I'm going to do this one more time here. This time, what's going to happen is I am going to go a T interval. And then I have my setup right here. I jumped straight to 1,000 this time. Sorry if you wanted to see the smaller cases, but you can see we're back at 99% like we're supposed to be. So this T distribution, mysterious whatever it is, we don't know yet, but it fixes the problem caused by putting S in for sigma, okay? This method up here would work, but it's unrealistic. So Z star is fine if we actually know sigma. But when you use S, you have to switch over to the T distribution instead. Okay? That's not a formal math proof or anything like that, but it should give you guys an idea of like what's sort of going on. So let's learn a little bit about the T distribution. We do more with the T distribution next chapter, and I get a little more detailed on it then. So I just want to teach you guys a few things about it right now because your heads are already going to be kind of swimming with everything else going on. What you need to know at this point in time, this bottom picture is the standard normal. So this guy right here is Z. This is your typical normal distribution for a series of data points here. And when you do a normal distribution, you see very, very few points that go beyond 2 standard deviations from the mean. You don't see many points with a z-score of 4 or something like that. And you can see that happen on this picture. The tails go really flat or pretty flat pretty quickly. The T distribution is like a cousin of the standard normal distribution. It still looks like a bell. It's still symmetric. But the difference with the T distribution is that the tails are a little bit fatter and it's not as tall either. So you get like a shorter kind of looking graph with fatter tails or more points within the tails of the picture. Okay? Yeah, there's a lot more area in the tails. You can see that we have plenty of points that go more than just the z-score, or in this case, t-score of -2 or -3. Why does this happen? Don't want to get too into that right now, but just a really quick explanation if you're at all curious. Let's say I had a list of numbers from 1 to all the way up to 100. So just all the numbers from 1 to 100. If you find the standard deviation of that whole list of numbers, it's about 29. Okay? So if you find the standard deviation of the list of numbers 1 to 100, it's around a 29. Let's say I took really small samples of like, I don't know, 4 numbers at a time. And I found S, your sample standard deviation. Say my sample ended up being just the numbers 1 to 4. S is going to be really low in this problem, probably like 1 point something. I didn't look it up, but 1.2 or something really, really small like that. Let's say my sample had a couple small numbers and a couple giant numbers, like this is my sample right here. S for this problem is going to be so much bigger, like 40 or something like that. So when we look at a situation where you're using S can vary quite a lot depending on how big your sample or what numbers you get for your sample and how spread apart they are. S is quite a bit more variable than what we're used to dealing with here. And when you get those crazy S's, you can get points that are far away from the middle. So you get more spread as a result. Like I said, a little bit of a simplification, but that's just to give you guys a basic idea of what's going on. If that was confusing, what you need to know is the t-distribution graph is shorter with fatter tails. You can still find a t-score similar to how you would find a z-score for a problem. So, like I said, we'll hit more on the t-distribution later on, but we're going to practice right now just learning how to use the t-distribution, and later we'll learn more details. So when should we use a t-star critical value rather than a z-star critical value for a population mean? You need to use a t-star when you sub in S, or S of x, in place of sigma. So if you happen to know real sigma, just like we did in that tomato example, cool. Do a z-star, it's going to be great. But most of the time, you're only going to have S, and that is when you have to do a t-star problem. Generally, since you won't know sigma, what really ends up happening is most mean problems require the t-distribution, where most p problems require the standard normal. There is a, I'll talk about that later, but just know that this is kind of the setup for that. How do we calculate the value of the t-star to use? You can use either a table, or there is a command on your calculator called inverse t, and I'll show you both of those in this video. And then there's one more thing going on I glossed over. I think it popped up on the last page and I just didn't address it. So t distributions use kind of an input parameter called degrees of freedom. DF is an abbreviation. My stupid thing keeps covering it right there at the bottom. But degrees of freedom are a vocab term related to the t distribution. And in order to find the degrees of freedom, what you do to get degrees of freedom is you take, for right now, you just take your sample size and you subtract 1. What does that mean? Why do they call it degrees of freedom? Like, what is even going on right now? Don't worry about it. We'll get to it later. What you need to know is that the t-distribution requires an input called degrees of freedom, and the degrees of freedom, all you do to find it is you go 1 smaller than your sample size, okay? That's probably confusing, and you're probably not seeing the point of it, and that's okay if that's where you're at right now. We're going to move on, and then we're going to look at some extra stuff with the t-distribution. So let's go ahead and learn how you calculate a t-star critical value. I'm going to show you 2 ways of doing this, both with the table and with the calculator, and look at both of them here so you can decide what works better for you. The basic idea here is that we're trying to make this tell you what kind, so a 90% confidence interval based on an SRS of size 10. When you're deciding what your critical value is, you need to know your sample size. They have to tell you that, or you can't do the problem. When we look at this here, the t-distribution is still symmetric, just like the normal distribution is, and we find the critical value in a similar way. This middle area here is going to be 90%, because it's 90% confidence interval, meaning that each tail is a 0.05. So if the sample size is 10, this weird thing called degrees of freedom is just the sample size minus 1. So there are 9 degrees of freedom for this picture. So in the tables that you guys got for your formula sheets, there's also these numbers right here, and we've practiced doing this with the normal distribution. If you keep moving back, flipping at pages in your thing, there's one for the t-distribution as well. And it gives you the right tail shaded up here at the top. So what I'm looking at along the top is the right tail, which I calculated as 0.05. So I want to be in this column right here. And I'm just going to match that up with the degrees of freedom, which we said was 9. So if you do that our t star is going to be 1.833 for this example. So t star equals 1.833. All right, next up, 99% confidence interval, sample size 75. If our sample size is 75, our degrees of freedom are 74. Our little picture right here has 99 in the middle, so that's going to be 0.005. And I'm going to pull up my table again. Now, they can't have a separate table for like every single number out there. So I've got my little table right here. And for this example, what did I say? 0.005. If you keep on scrolling in this table, what you're going to find is that after like 29 and 30, they don't do every single number. That would take way too much space. They just start skipping around. So if I have 74 for my number right here, I cannot bump that up to an 80. Bigger sample size means more precision. So that would be basically making a more precise ruling than I have the right to do. So you always conservatively drop it down to the number below that, which in this case would be the 60. So I'd be looking at 2.660 for my number on that problem, 2.660. So you may decide that you like that better, but many of you will probably opt for the calculator, which is cool as well. The calculator is super simple. All you're going to do, it's a lot like doing the Z-star. In that same menu, the distributions menu we've been to many times, the distributions menu has an option called inverse t instead of inverse normal. If you choose inverse t for our first one, we had 0.05 and our degrees of freedom were 9. And it'll give you a more precise decimal than even the table, but you can see 1.833, same thing. The negative, remember, you can just drop. When you do the second problem, though, this one is going to be a little more precise, actually, because we had to bump down our sample size in the last one. So I need 0.005, degrees of freedom was 74. And the calculator will give me an even more precise estimate of 2.6439. So T star 2.6439, I think it was. And this was with inverse t on the calculator. So finding a critical value, not that bad, just a different table or a different button on the calculator. So when we make confidence intervals for mu, there are going to be 3 conditions we check, just like there were in the last section with p. One of the conditions is still going to be an SRS. One of the conditions is still going to be our 10% condition, but there's going to be one condition that changes. Instead of large counts, n times p, n times 1 minus p, think if you can remember what the last one is, I've already said it in this video once. It is going to be either that the population is normal, or it's going to be that the sample size is greater than or equal to 30. That's called the central limit theorem. So that is going to be our new condition that we have to check. The standard error of the sample mean, remember standard error is when you plug in what you get from your sample. So instead of looking at sigma divided by root n, we're going to have s divided by root n. And if you look on your formula sheets on that second page, we had our p formulas right here. We have our X bar formulas just below that. Standard error, s divided by root n. I wrote s of x. Let me fix that actually. That's going to be s of x. I'm missing my bar on this guy right here. Okay, so the formula for a confidence interval, the actual formula you will use is what we learned under method 3 with the tomatoes earlier in the video. You have your X bar. You do a T star, and then you multiply by s over square root n, or s of x bar. So this is going to be our basic setup for the confidence intervals. Now this video is running a little bit long here. I'm packing a lot of info into this. The next part of this section should be quicker, but I want to finish things off by basically walking you through how to do one of these 4 steps. So for these 2 girls' second semester project, they decided to look at the weight of Oreo cookies and see if it was what they advertised it should be. So they say to construct and interpret a 95% confidence interval for the mean weight of an Oreo cookie. The first two things you do are define your variable. We want to estimate blank with a 95% confidence interval, and then give your conditions. I'm going to throw those up there. So try that yourself and pause me and get that, just see how you do with the practice. All right, so I have my variable defined in blue, and then I have my conditions in this pinkish color right here. One comment on the conditions, and it's for the central limit theorem condition. We don't use a normal distribution for this problem. We use the t-distribution. So all I did after I said, oh, my sample is greater than 30, I just said that the t-distribution is appropriate for the problem. So because we're using a t-distribution, if your sample is large enough, you can use the t-distribution. Now it's time to actually calculate our interval. And in order to do that and make our calculations here, I'm going to start out by, we're going to end up using a little formula. The first thing I'm going to do is I'm going to do an inverse t on the side to figure out what my critical value is going to be. If you have 95%, the tail is going to be 0.025. So you would do an inverse t with a left area of 0.025. And the degrees of freedom for this problem would be 35. Make sure somewhere in the problem you mention the degrees of freedom as well. So I've got the degrees of freedom is 35. And now I'm going to go ahead and do my calculation. So it goes x bar first. My sample mean was 11 point whatever. So 11.3921. Plus or minus, when you do your inverse t command, you should get 2.030 times your sample standard deviation of 0.0817 divided by square root of sample size. Don't accidentally use the 35. It is an n right here, so you put a 36 for this part. Then what I would do is I would just multiply all this, get your margin of error after the decimal, do your plus or minus. I'll write that up there, and then write your conclusion as well where you interpret the interval. So pause me while I pause this and write it down yourself. All right, so I've got my work on the side, and then I've got my conclusion as well. We're 95% confident that the true average weight of an Oreo is between 11.364 and 11.420 is what I got. When you write your conclusion, the single biggest mistake I see it all the time. Make sure you mention the word mean or average in your answer. If you forget to write mean and just say, oh yeah, the weight is between 11.36 and 11.42, just like the weight or something, you will lose credit. We're making an interval for the mean weight. So that word mean or average has to be in your answer, okay? So these aren't that bad to do once you figure out all this weird stuff with the t-distribution. Final thing, on the package, the stated serving size is 34 grams for 3 cookies. Well, if I divide that out, 34 divided by 3 is 11.33 repeating like that. Does this interval above provide convincing evidence that the average weight of an Oreo is less than advertised? So these girls went into this problem thinking Oreo was lying and they're saying their cookies are heavier than they actually are. It turns out, though, when they actually conducted their research, they found the opposite. 11.33 is not in that interval above. All the numbers in our interval are actually bigger. So we actually did the opposite, and we found convincing evidence that Oreos are heavier than they're advertised as, okay? So I will put a little written thing for that, and then we are done with these notes. Hopefully you guys can read that. It says they found convincing evidence that Oreos weigh more than advertised.